Ricochet. Oh, your heat behind. Oh, your mask of lies.
Hello guys, today we're gonna talk about a energy transfer through the air. It's a bit windy and it's raining outside, so maybe there will be some lightning. But anyway, let me just start with this. Okay, so here I have a two MOSFET driver with a push-pull configuration. I have a gate drive transformer with Zener diode protection. They are in series, but they are turned each way, one to another. I have just this capacitor right here. I had this capacitor to start up, but I don't need a electrolytic capacitor because its resistance for this frequency is too high. It is operating in frequency range from around 8 megahertz to around 10 megahertz. It is resonating at the frequency that we're gonna choose with the objects that are surrounding it. So if I put the hand near it, the resonant frequency can drop within a spectrum of about half megahertz easily. So it is self-oscillating, and this is challenging because you need to have a right amount of voltage and current going back into the circuit that it could drive it again. But by changing the conditions on the top load, you can take too much current so it shut down, or you can short it anyways in any other ways. It can be problematical. There's no ICs right here, no voltage regulator to step down this. With these two MOSFET RF 450 that are rated for I think 400 volt. We are just supplying 20 volts inside. It's a bit of sawtooth because there are just smoothing capacitor. This is no stabilization right here because those spikes can get to about 30 volt on the supply rail. So we are not sure that we could use some buck or boost converters or linear voltage regulators, because this can mess up your power supply quite a lot. So the recommended is to use a transformer with a bridge rectifier and some smoothing capacitors. As you can see, with this potentiometer that's 100 kilo ohms, we are just supplying the voltage to the gate of the MOSFET, and the Zener diodes are getting just a bit current through. So there is a voltage divider. At some point, as you adjust this potentiometer, the voltage on the gates is gonna be high enough to turn on the MOSFETs, and the oscillation will start. So here I have a gate drive transformer. I use two droids, just small. I bought them on AliExpress, and this is just enough to turn on these gates. I had a gate transformer before this one. This is from the computer, the main choke on the input of the computer. As you can see here, we have some main chokes right here. This one is this green droid. As you can see, it's green. This is good materials. There are some others that are used in ATX power supplies on the end when you have just these spikes to get spikes away. I don't recommend those cores. Those here and here, they are not very good, and the ones like these, don't really use them, because the energy that is needed to open the gate through this is not very good. I mean, they are made differently. So I don't even use the transformers that are used for for switching power supplies. I never tried those, but they may work. So I tried this transformer. This was wind for IGBT, for high power IGBT drivers, but I just use this one. This one it can be just perfect. But for this operation, I use those small ones because they don't transfer too much power, so Zener diodes don't get hot and melt the solder off. Okay, so let me just get started now. As you know, we have a MOSFET driver to drive this transformer, Tesla coil transformer. There is no core. There's just a air. We have here a similar wind transformer, similar, not just a visual, but similar, as you can see, the turns, number of the turns, and the capacitance of the top load is very similar. There is no perfectly similar one. More similar than they are, the higher efficiency you can get. And as you can see here, primary is 1-to-1 ratio push-pull configuration, and here we have 3 turns, so we have 3 times higher voltage here than here. So if we have oscillation with 15 volts on this side, we can get the 45 volts here, but the voltage drop will be, because of efficiencies, everything is going to be so low that it will barely turn on the incandescent light bulb. So if I turn this on, as you can see, we have here one, and this is the second one. I have the power supply that the minus is not connected to the ground, but the ground is connected to this one. So this one is connected to the minus and this one to the ground. They are 100% galvanic insulation between those two transformers. Just the earth, they have the same earth, so deep inside they have the same earth. I should just put some wires in the ground outside, but it's too difficult right now. It's raining outside, and okay, let me just start it up. I will put it to around you can see the electricity is going out a bit, so I will turn this up to about around 20 volts right now. Okay, now oscillation is being started, so we can see the light bulb is just barely turning on. As you can see, we can pull some sparks out of here. Let me just turn this off a bit, so the light bulb turns off. As you can see, there is no connection. We have just three turns of a copper wire connected to the light bulb. It is 21 watt 12 volt light bulb. So let me just get this a bit further. As you can see, right now it is about 2 centimeters further. So maybe I have a ruler right here. Yes, I have a ruler right here. It's a bit damaged, but the distance between those two coils is around 15 centimeters. So with a 15 centimeters, let me just turn this on. Okay, the oscillation start. This light bulb is not turning on right now. We can get some sparks out of here, but light bulb is not turning on right now. It may be just heat a bit. Yeah, maybe you can see this just heat a bit. You can get a resonant frequency the right way, and you can see when I'm changing resonant frequency, the light bulb is lighting a bit, but I'm getting zapped right now. You can see we can turn on the light bulb, but how we turned on the light bulb is because we match the resonant frequency of this one to this one, and as I said, when we match the resonant frequency, the energy transfer is bigger. When we talk about a transformers, we don't really want some resonant frequency to be created. When we talk about the high power and stuff, like motors, like a house electricity, we want zero resonance. So the other stuff like computers, telephones, charging stations, everything should work with a smooth sine wave of 230 volts in my country. So as you can see, we can get this starting, but we need a bit lower resonant frequency right here. So when I add my hand near it, the resonant frequency dropped, and the resonant frequency were matching they were matching slightly more, and this turned a bit on. So if I bring it near, right here, I don't want to bring it too near because the spark can occur between there, and if I turn this on, you can see the lamp will start glowing quite bright. So let me just turn this on. Okay, it's turned on right now, and you can see it is quite a lot of power right here.
Wow!
You can see the light is quite powerful, and if I measure resonant frequency even more, it gets even brighter. I'm afraid to touch it because it does not shock you because of high frequency and skin effect. It just burns your fingers. So you can smell a roasted human flesh. But okay, let me just put it one more time away. Okay, let me just start this. I have here scope, so I can see I have probes hanging around, and I can pitch the oscillation. Otherwise, I could kill this. Let me just show you the sparks that are created here. So resonant frequency starts here, and as you can see, we can get those. Oh, it shuts down. Okay, now it will go. Okay, now we can do it. So right here we are at the resonant frequency. If I go closer, the capacitance is too high, and it shuts down. You see, here is the maximum I can get. And when I move hand farther away, it slows down. So I hope you can see this. Here is brightly, shining very brightly. With this heatsink, maybe I can adjust it a bit more. Yeah, right here. So let me just turn this on. Check the temperature. Okay, the MOSFETs stay cool. That's quite nice to see. Let me just put it backwards one more time, and let me try this time. So, what is the main point we want to tell about this right now? So, the main the main disadvantage of the energy transferring through the air is that the efficiency of energy transferred to the distance drops by a square. For 1 centimeter we have 100 watts transfer of energy, and for
2 centimeters, there ain't gonna be half as low, but it's gonna be just 10 watts. So
I should not be here with this hand. This should be perfectly like this. And now if I put it inside here, and if I touch the ground, it's gonna be even better. It glows a bit, but when I put the hand in between, it stops. But with the same hand, I can get it to the resonance frequency, just about the perfect resonance frequency. So you can see it is pretty powerful. It can melt this metal. You can see the metal is being melted. It is red, hot glowing, and it can create a lot of noise if you want. I will even try to get it to play some music or something like this. I have some bigger Tesla coils laying around right here, some primaries. It's a bit of mess here, but you get the point. There can be energy transferred through air, but it's very inefficient way.